Greetings and welcome to Distant. In today's video, we'll be talking about linear regression. It's a very simple and yet a very powerful tool in numerical mathematics. So let's talk about that. And one reason why I am dealing with linear regression is that it is going to be very useful for a few chemical engineering applications. So in the next few videos, we'll be talking about using linear regression to, let's say, predict rate constants of reactions and so on, right? So what is linear regression? So basically, it establishes a linear relationship between two variables. So let's say we have two variables, say x and y. X is what we'll call as the independent variable, or we could also call it as a feature. And y is what we'll call as the dependent variable, or we could also call it as a target variable. Right. So let's say we have data sets of two variables, x and y, right? So what linear regression does is it um, tries to establish a linear relationship between these two variables, a relationship that is given by the model y equals to beta naught plus beta 1 x. Okay. And over here, beta naught and beta 1, these can be termed as the parameters for this linear equation. Okay. These can be considered as parameters for the linear equation. Okay. So this establishes a linear relationship between my target variable y and my feature x. So this is a simple linear regression. We can also extend this to multiple features. So for example, if I have established a linear relationship between n such variables or n such features, so we could say this can be written as this, right? So as long as all of your features as well as your target variable have a power 1, we'll call it a linear regression model because we are trying to establish a linear relationship between all of these variables, right? Okay. So now, naturally, this is a model. Therefore, whatever we do with this model, we'll be able to predict the value of our target variable based on the values of features that we already have. So that is what a model does, right? So let's say let's just talk about one variable linear regression or a simple linear regression right now because uh, the multiple linear regression, this is known as a multiple linear regression model. The multiple linear regression model would use a lot of matrix operations. And right now, I would not want to go there because we are still getting started with that. So let's just talk about a simple linear regression. So we have this model y equal to beta naught plus beta 1 x, right? That is the model, right? So let's say we have a given data point xi comma yi. This is a data points that we have. Okay. Now at this value of xi, we'll also have a predicted value of y using this model, right? So we will say that y predicted, we'll call it as yi cap. All right, this is the predicted value. So yi cap is simply beta naught plus beta 1 xi. So that is the value of the target variable that has been predicted by the linear regression model that we used, right? And the actual value that we have, which is y actual, is the actual data point that was given to us. So that is yi, right? Now, these two would definitely not be the same. There would be some sort of an error between the two of them, right? So that error is given by yi minus yi cap, or yi actual minus yi predict, right? Now, these errors could be positive or negative, right? But if we just want the errors to be positive, one way could be we take an absolute value or a mod of this. But a more efficient way that has been seen is that we take a square of these errors. All right. So we'll take a square of these errors, right? And for all possible data points, so let's say this is just for a single data point. So let's say if we have n data points, so for all possible data points, the sum of squared errors, which we are going to call as SSE, is going to be the summation of EI square from I equal to 1 to n, right? And naturally, we want this model to predict the actual values as well as possible. And therefore, we would want this sum of squared errors to be as low as possible. So we would want to minimize this. We want to minimize this, right? And how do we minimize this? We would minimize this with respect to, there are two parameters that we have, beta naught and beta 1. So we can manipulate, or we can change the values of beta naught and beta 1. And we'll select the value of beta naught and beta 1, which is uh, or basically which minimizes the sum of squared errors, right? So if I make write this in a better way, so EI square can be written as yi minus yi cap whole square. And yi cap, from here, we have written it as beta naught plus beta 1 xi. Okay, so yi minus beta naught minus beta 1 xi whole square, right? And let's call this as SE. So we are trying to minimize SE with respect to beta naught and beta 1. Okay, so now this becomes quite simple. In order to minimize any function with respect to two variables, what we need to do is we need to take a partial derivative of these two, or basically we'll need to take a partial derivative of uh, this function with respect to the two variables and set those partial derivatives equal to 0. So let's take a partial derivative of SE with respect to beta naught, keeping beta 1 constant. So in that case, we get this equal to, now we'll use a chain rule of differentiation. So we could write this as summation I equal to 1 to n 2 times yi minus beta naught minus beta 1 xi, right? And multiplied by minus 1, because the derivative of the inside function with respect to beta naught is minus 1, right? And that has to be equal to 0, which makes our equation as summation yi minus beta naught minus beta 1 xi equals to 0, because 2 and minus 1 can simply be taken out of the summation, right? And now we can open up the summation. So we have summation yi minus summation beta naught minus summation beta 1 xi equals to 0, right? Now beta naught and beta 1 are constants. So they do not change with I. So we can bring them out of the summation. So we'll have summation yi minus beta naught summation 1 minus beta 1 summation xi equal to 0. And this can further be written as summation of yi minus beta naught times, we are summing up 1 capital N times. So this simply becomes capital N minus beta 1. And we are summing up xi. So that is this. Okay. So this is one of the equations which relates beta naught and beta 1. Okay. So this is equation number 1. All right. Similarly, we have the partial derivative of the function se with respect to dou beta 1, right? Keeping beta naught constant. So once again, this becomes 2 times yi minus beta naught minus beta 1 xi. And this time we have to take the derivative of the inner function with respect to beta 1. That is going to be minus xi. And that is equal to 0. So once again, minus 1 into 2 can be brought out of the summation and we could just remove that. So we simply end up getting summation and we'll now multiply xi inside. So we get yi xi minus xi into beta naught minus beta 1 into xi square equals to 0. And if we break open the summation, we get summation xi by I minus beta naught comes out of the summation. So beta naught summation xi minus similarly beta 1 comes out. And that is the second equation that relates the two. Right. So now the values of beta naught and beta 1 that satisfy these two equations are going to be the ones that minimize my function se, right? So there are two equations and two variables. These can be solved easily. So if we just solve for, let's say, beta 1 by eliminating beta naught from the two equations. So we could do that by doing this, right? So if we subtract 1 by n and 2 by x, summation xi, so beta naught gets eliminated. So we get summation yi by n minus beta 1 summation xi by n minus beta naught from the first equation. And then we are subtracting the second equation. So minus summation xi yi by summation xi minus beta naught. So this would be minus into minus, that is plus. And similarly, plus beta 1 by summation xi into summation xi square is equal to 0. And beta naught and beta naught get cancelled. This becomes yi bar or just y bar, which is the mean value, minus beta 1. This becomes x bar, right? This is summation xi yi by summation xi. And this is plus beta 1 summation xi square by summation xi equals to 0. And from here, we'll get beta 1 equals to y bar minus summation xi yi by summation xi whole upon x bar minus summation xi square by summation xi. And we could bring this to a general form by saying this by just taking an LCM of the numerator and denominator. So we'll get summation xi times y bar minus summation xi yi upon summation xi times x bar minus summation xi square, and summation xi gets cancelled from the numerator and denominator altogether. And this, if we divide, let's say, the numerator and denominator by the total number of data points, so we get summation xi by n, which is x bar. We can write this as x bar y bar minus summation xi yi by n upon x bar whole square minus summation xi square by n, right? And that is beta 1. You could find other formulas for beta 1 as well, but all of these can be manipulated to get those forms, right? So this is the form that I have derived, and this is what I'll be using. But all other forms that you see in different books or any website or any other video, all of them can be obtained by this sort of an exercise. You'll just have to do some algebraic manipulation here, right? But anyway, we've got beta 1 here. And then if we go to equation 1, and we write this as summation yi by n, which is y bar minus beta naught minus beta 1 x bar equals to 0. So we simply get beta naught equals to y bar minus beta 1 x bar, right? So that is how you obtain beta naught. So we've got beta 1 from this equation, and we can obtain beta naught as y bar minus beta 1 x bar. Okay, so we've obtained the two parameters, beta naught and beta 1, right? And now we can just put these parameters in our model. Y equals to beta naught x plus y equals to beta naught uh, plus beta 1 x, right? So we can put it up here. And for any given value of x, we'll be able to predict a value of y. All right. So that is one thing. Now, in this case, you'll see that the sum of squared errors would be the minimum for these given values of beta naught and beta 1, right? So we've shown that sum of squared errors is given by summation yi minus yi predicted whole squared for all the data points, right? There's another quantity which is known as total sum of squares, or uh, we'll call it SS total, or simply ST, just like we call this as SE, right? And that is just total sum of squares, which is summation yi minus y bar, right? Whole square. So this basically shows you the difference between any given value of yi from its mean, right? Or how spread out your data is. This gives you an information about that. If you remember, this is also how you get the standard deviation. So this, if you remember, in the previous video, we talked about variance, which is nothing but summation yi minus y bar whole square upon n. Right, that's how you get the variance. So this is basically a way in which you can, and variance tells you, or standard deviation tells you how spread out your data is. So this is a measure of how spread out yi is uh, around the mean y bar. Okay. Then we have a parameter called as coefficient of determination, which is r squared. And r squared is 1 minus sum of squared errors upon total sum of squares, right? And this can be positive, zero, or negative. But it has to be as close to 1 as possible. Okay. So for r square equals to 1, it is considered as a perfect fit, right? So it has to be as close to 1 as possible. But it can be negative as well, which means it is a very, very terrible fit. Okay. And r square actually tells you the goodness of fit. Okay. So it has to be as close to 1 as possible. So r square tending to 1 would imply a very good fit. And that implies that the model is acceptable, right? So we'll see later on that um, r square may not be the best parameter to evaluate which model is the best, but definitely it is a good start. And in most of the cases, at least the examples that we'll be discussing, R square is a good enough indicator to ensure that we are using a correct model and the predictions we will be getting from this would be very reliable. All right. So this is the theory of linear regression. So once again, I'll just summarize it over here. We have two variables, x and y. We have data points in x and y, which are represented by xi and yi. And we have n such data points. Okay. So linear regression gives us a linear relationship, or it's a model which establishes a linear relationship between between the variables x and y. All right. And in order to establish this linear relationship, we have to show that the predicted value, which is yi cap, which is just beta naught plus beta 1 xi, minus the actual value, the square of this, and when we add it for all data points, this has to be minimum. This has to be minimum with respect to both of the parameters used in linear regression, which is beta naught and beta 1, right? And when we do the minimization exercise, we get beta 1, which is this, and we get beta naught, which is this, right? And based on that, we can get the predicted values. Now, we can also calculate the total sum of squares, which is summation yi minus y bar whole square. Remember, yi is not the predicted value here. This is the data point or the actual value. When we get the total sum of squares, we can evaluate the parameter coefficient of determination or r square, which is 1 minus SE by S total. And this tells you the goodness of fit. If it is very, very close to 1, we'll be able to predict that this is good enough, right? We'll be able to say that the model that we have used is good enough. Okay, so in the next video, we'll use linear regression for a few chemical engineering applications.